Hello everyone, welcome to cppvalley. So today we are going to understand everything about smart pointers. So we will understand about unique pointers, shared pointers and weak pointers, and we will deconstruct them in great detail. We will understand how we can have our own implementations of different smart pointers. We will understand which smart pointers are actually used in production, which smart pointers does not add overhead to our program, and uh, and how these smart pointers maps to different use cases. Then we will also understand uh, the associated concepts on which smart pointer is based on. So this is going to be a long lecture, but once you do this lecture, you will have a very clear picture and in very in-depth understanding of smart pointers, which is very essential that you get a hold of this because uh, it is related to memory management and so and resource utilization, which is a constraint in many critical softwares, critical web applications, and yeah. So now to become enterprise grade software developer, you must not only understand the construct of smart pointers, but also you need to know how you can customize your smart pointers and how you can actually use your own allocator, use your own deleter and all those things with smart pointers. So let us start. We will start from scratch and take it to a very in-depth level. And yeah, so this is going to be a long video. Make sure that if you have started watching, make sure you watch it completely, because I'm not going to miss any concept. So after watching this video, one thing you can be sure is you don't have to look around for resources on smart pointers, because whatever I'm teaching, I have taken references from different C++ distinguished authors also, be it Scott Mayers or some code snippet from Anthony Williams books, etc. Okay, so let us start. So let us write a simple program, and we are going to use raw pointers, and then we will try to understand the behavior of the program. So let us say you have a function int. Let us make it void. Void func. It does not take any argument. All it does, it creates a pointer. Okay, and yeah. Okay, now we have a new int statement here. So what it will do, it will allocate the memory on the map. So whenever we do new, so this is internally what is happening is it is basically calling the operator new, which will allocate you some memory. So it will use the standard allocator, and it will allocate you memory, and that memory is allocated on the heap, and you get a pointer to that memory. Okay, now when this program runs, if you see, the memory was allocated on the heap, and p is a stack variable, right? Now when the program ends, everything is destroyed, but not your heap memory. Why? Because you did not deleted p. Okay, so the programmer must manually call delete on this p, and if we forget, then the memory will leak. If we try to delete it twice, then that would be undefined behavior. And if exception happens before delete, then again delete will not happen, right? So the program will exit even before the delete will happen, so that will cause the leaks again. Okay, so let us say I do in this, let us make it a global variable, and when I say p is equal to new int, I'll just print the value of p. Okay, and let us add a execution for this. Mm, mm, this is there, and let us try to print p. Okay, let's print it, then we will see what happens. So it is printing 10. Now let us do delete. Delete p will delete the memory which was allocated. Okay, now if you do this thing, it is now printing some garbage value. Fine, because the memory was already deallocated. Fine. Now let us see what happened if we do double delete. So when we are doing double delete, it gives us this error that double free detected. Okay, so this is again a undefined behavior. Now the compiler will assume that the user will not even try to delete the heap memory twice. Okay, and now the compiler will assume that okay, this was not your intention, and hence I will assume that this was never done, and hence I will optimize it the way I want, and that is called undefined behavior in C++. Okay, so that is about it. Now just look at this scenario. Let us say we added a exception after we are printing the variable. Let us say that, let us first remove the double delete and add a throw exception. So we are throwing exception at this point, meaning before deleting the pointer we are throwing exception. And let us add the header for exception, clue exception. Okay, so now what is happening? The function func will allocate memory on the heap. Cout is printing the value, and then what happens? So now if you see, what is happening is after the memory was allocated and then we are trying to print, then we are throwing exception. So the behavior should be like, since we already threw exception, this delete will never happen and it will be a candidate for memory leak. Okay, now if you see in the right hand side, the output is not printing the value of dereferenced pointer. And why is that? This is because when you do a cout, this is basically at the kernel level, it will translate to a system call which is write, and when you do cout, the output is generally stored in a buffer. Okay, and once the buffer is flushed, then only you see the output on the screen. So basically this is an optimization technique. So rather than calling the kernel function write, kernel syscall write every time, what it does is it keep on accumulating all your couts, and then at once it flushes, means it calls the write function, write system call, and then it prints on the console. Okay, then how you can flush? You can flush if you have a new line, if you have a end line, then then it will flush. Okay, so just to make you visualize, I will add an end line here, and if you see, now it is printing. Okay, if I remove this thing and I do this thing again, okay, so if you see, right, this is not printing, this is accumulating the values in its buffer, and only when it will be flushed, okay, then only it will print. Basically it is reducing the number of write calls. Okay, so this is done, and now we are throwing exception, meaning this will never run, the memory will be leaked. Let us try to change the code a little bit. What I'm going to do is, I am yeah, so instead of doing it in main, let us print here. So I will do cout star p and then flush it, and I will throw the exception in the function function. Okay, and here it is delete. Let us remove these things from here. Okay, so fine, the expected behavior is it will print 10 and then it will throw exception. Fine, now let us try to control the flow of this exception. Okay, so whenever exception is thrown, the ideal behavior is to catch that exception so that the program should end gracefully, and any cleaning task that we want to perform, any post exception task that we want to perform, we would normally do it there. Okay, so let us use try. So I'm saying that you try to run this function. Okay, and whenever you catch exception, you come here and execute this code. So I'll say that exception catch, new line to flush, retry function catch. Catch is a function, it takes, let's say it will take the exception. Okay, so it is printing exception caught because we are throwing an exception here, and we can do it delete p. Okay, so now now it will get deleted. So but you see, right, this is a manual effort that we need to do. So what are the efforts involved here? First, we did a try, and then we did a catch, meaning if this will go wrong, we are going to have some handle mechanism, and in there we are going to delete the allocated memory. Okay, now to solve this particular problem where a raw pointer can cause issues, like we already discussed, that manual intervention is needed. Double delete will cause an issue, because when you're writing a complex project, you will pass pointers generally within interfaces and functions, and it becomes difficult to keep a track of the number of times you are deleting it. And if you ever try to delete it twice, then you will have an undefined behavior. If exception happens, you will leak again, and you cannot go on writing try and catch for every allocation. Okay, so the C++ standard, the modern standard, says that your resource should be tied to object lifetime, and we will understand about this. And this very concept is called resource acquisition is initialization, meaning the C++ wants you to have a kind of mechanism where whenever you run a constructor, you acquire a resource, and whenever you run the destructor, it releases the resource. Meaning, a constructor will always run in pair with destructor. And if you are creating an object, and during creation, if you are creating some resource, then this is very deterministic that the deconstructor will also run, and in deconstructor the acquired resource will be released. And this is the very soul of smart pointers. Okay, so let me get rid of this program. Okay, so our goal is to come up with the wrapper, which we will call a smart pointer, and we will tie the resource to the construction and destruction of that object. Okay, so basically where we want to reach is, we will have, let's say, some unique ptr, and let's say it will take some, it will be templated, meaning it can point to integer, character, double, etc, and we will have p equals p, and it will be initialized, constructed with a raw pointer. Okay, let us write this like this. Okay, so now this unique pointer is a custom pointer that we will create. This is the type that it will take. This is the object of this unique pointer class, and then we are initializing it with some data. So this here the constructor will run, right? This is a plain simple code. Let's say you just remove this also. So you are saying that you will have a class which is unique pointer, the name with unique pointer. You will create an object of this class, and then you will do some initialization. Okay, now when this p goes out of scope, the destructor will run, and then the destructor itself will do delete, and hence the memory is automatically freed. Okay, that is the core idea of how we use smart pointers. Okay, so basically smart pointers are the implementation of resource acquisition is initialization. Okay, now let us try to build whatever we have written. Okay, so we are saying that we will have a class with a name unique pointer. So let us create a class with name unique pointer. Okay, now we are also saying that this will take a raw pointer. Okay, meaning it should have some constructor. Okay, and since we are able to create object from outside, meaning the constructor has to be public, and hence we have written is public. Now create the constructor. This is the constructor. It will take a pointer, and it's what it is going to do. It is okay, so let us say that we had a ptr here also, and now what will happen, what we will do is we'll say that okay, so this ptr will be equal to p. Okay, so and then what we want is, now when destructor runs, destructor for this unique ptr run, because whenever p will goes out of scope during stack and winding, the p will get deleted. When p is deleted, delete p will invoke the deconstructor of the type, which is unique pointer. So let us write the deconstructor. Deconstruction does not take any argument, and here what we are going to do is we will do delete this ptr. Okay, so we have our own unique pointer now. So this unique pointer will create a pointer p, and it will delete that very location in the heap, right? So what essentially we are doing is, during the construction we are creating the resource. If you see, we are doing new int, and we are storing it in, let's say, pointer ptr state. So this is resource acquisition happening in initialization phase. Now when the destructor runs, when P goes out of scope, the destructor automatically runs, and we have written delete PTR. So it automatically cleans the memory, preventing memory leak. Fine. And now if you see, we are passing a type of integer pointer. Okay. Now what if we want to pass a pointer of type, let's say, let us assume you have a class book. Okay. And you are saying that I want a unique pointer or a smart pointer of this book class. And let us say this is a book object, book PTR to be very precise. Okay, now it will give us error that there is no function call to unique PTR books, meaning we do not have a constructor that takes this that very argument. Okay, now let us write that also. So when we write this, you will see that the error will, so we had one more constructor and the error will go away. Fine. Now assume that we want to create a pointer of some other type, let's say double or character or string or whatever, or some new class. Then we won't be writing again and again. We won't be adding the that very constructor with that very parameter. That is bad code practice. We should not touch what has been already established. Okay, what has been already tested and tried. And there comes the templates. Okay, so we will say that whatever the type you will see, let's say t, whatever t comes, you create a pointer. Okay, so we will have a raw pointer of t, and let us in the constructor take t. Okay, so now we are giving a generic type, right? Now if you see, the error goes away, meaning whether you pass a integer, you pass a custom class object pointer, the function is going to, the class is going to accept everything. Okay, meaning this constructor is going to handle any type. Okay, and this will happen at the compile time. Okay, so if things happens at compile time, then when you run the program, there is no overhead involved, right? And if there is no overhead involved, then that is a good code. Okay, so this is about it. We have reached at this stage that we have a pointer which we are owning ourselves. Okay, like we are constructing and we are in the deconstructor we are deleting, so the ownership has come upon us. Okay, and also that the acquisition is happening in initialization and the resource freeing is happening in the deconstructor. Okay, now let us try to print the value of t. Okay, so whenever we do, let's say cout and let us do t. Yeah, let us, I mean, not the unique PTR object itself, let us print the pointer, the value at the memory. Okay, and it should have printed as 10, but since your compiler or the cout is not understanding that what actually is p, what actually is star p. Okay, so it is similar to that. If you have two classes and if you want to add those class using the plus thing, add the object of those class using plus thing, the compiler will not understand, right? In those cases, what you do is you overload those operators, meaning you try to change the behavior of those operators based on your use case. So again, we need to do some overloading here, right? And what do we need to overload here? We need to overload the asterisk operator. Okay, so the I assume you know the syntax. So we have some return type, and we say that okay, so operator is asterisk that we need to overload. Fine. And what we want to return? We want to return the value, so we will dereference this PTR. Fine, so this will be int, and now it prints 10 because we have overloaded the asterisk operator. Okay, since we overloaded the asterisk operator, now this asterisk understands that if I have to dereference this p object, what I need to do, basically I will call the operator asterisk function from the class of which p is a type, meaning p is a type of unique pointer class, and this class has implemented or overloaded the asterisk operator. So now, even though p is not something that asterisk already understand, it will now try to find the implementation of asterisk inside this class. And here we are doing this. Remember, this dereferencing is allowed because this is inbuilt, this is primitive, right? But with a custom object, you cannot do dereferencing directly unless you overload the functionality. Okay, so this is fine. Now let us also overload some other operators. Let us say that we have overloaded this point to operator, and then when we do that, we want to just return the pointer, and since pointer is of type int star, let us return int star. Okay, it is fine. And here also let us return a so let us return this reference rather than returning the value. Okay, because it will unnecessarily do some copying which we don't want to do. Okay, so this is where we have reached till now. We understood how we can create a unique pointer class, and now when this program runs, you don't have to do anything because the delete is taken care in the destructor. And yeah, so this is a base that we have created. Okay, now before moving forward, before doing more implementation in this, the class that I'm trying to implement is unique pointer. So in C++11, it came up with 3 smart pointers for different use cases. The first one is unique pointer. So unique pointer means that there will be a single ownership, there will be a unique ownership of the object, of the memory. Meaning, if you have to copy that pointer, copy the that very, let's say here it is p. If you have to copy it to some other variable, you cannot do that. You cannot copy it. Meaning, the ownership is with p. You cannot copy to p2. If you have to copy to p2, then that would be a move operation. You'd have to move the ownership from p to p2, and that is how the invariant of unique ownership is maintained. Okay, that is one thing. Then we have shared pointers. Shared pointers, you can do a copy. They are essentially existing so that we can have a shared ownership of a very particular object. And we generally don't use shared pointers because it also comes with some overhead, some fallbacks, and some problems that we will see later. And third comes the weak pointers. Weak pointers are basically introduced to take care of the problem that comes with shared pointers. So in shared pointers, we have a problem which is like cyclical dependency problem, and that cyclical dependency problem is solved by using a weak pointer. Okay, so weak pointer is basically just observer of a particular memory. It does not own the pointer. It is just a observer pointer. So these things we will see later. So right now, whatever we are studying is pretty much basic. Okay, we have not even gone to custom deleter and custom memory allocators and how multi-threading can cause a problem and all those things. We have not even gone there. We have not gone to move semantics and all those things. This is pretty much basic. So if, let's say, now that we are dealing with unique pointer, if you do something like this, let's say you have a unique pointer of int, you say p2, and if you try to do this p1, let us see what happens. Sorry, p only. Okay, now let us try to print this. To print this p2 also. Okay, let's see what happens. So it is printing 10 and 10, and when the program ends, it is giving you an error that there is double free detected. Why? Because whenever you do p2 is equal to p and your class is having a raw pointer, meaning it has a pointer to a memory which is on heap, and when you do this p2 is equal to p, the compiler will try to insert a copy constructor by itself. Okay, so since p2 is being constructed for the first time with the help of p, the compiler will implicitly add a copy constructor, and it will do a member wise copy, meaning in p2 it will see that okay, for every instance of unique pointer I will have a data which is a pointer, and then it will add a copy constructor, and there it will just copy the pointer, it will not copy the exact values, and which is the shallow copy problem. Okay, it will not do a deep copy. To do a deep copy you would have to implement your custom copy constructor. Okay, that is the only way. And now since both ptr in p2 and p are pointing to the same memory location, when your program ends, when p2 and p both goes out of scope, the destructors of p2 and p runs, and in the destructor for both we are doing this delete ptr, and hence you see a double free. Okay, and since this is unique pointer, what we wanted is we wanted a unique ownership, meaning whenever the compiler should see this statement, it should say that okay, this is not allowed. How can we do that? We can do that by not allowing the compiler to insert copy constructor, by not allowing the compiler to even allow a user to write a copy constructor. Okay, something like that. So let us try to delete the copy constructor. Let us explicitly delete the copy constructor. Okay, before that, you know what a copy constructor is, right? Copy constructor is basically a constructor, and where we are overloading the equal to operator. Okay, and it will take a unique ptr, let's say p, and this takes as a reference. So take it as a reference because we are creating a copy constructor, and we cannot again take p as a copy, right? If you write just p without using this ampersand, it will again invoke the copy constructor, and which we are writing right now. Okay, so that would be some recursion that we want to avoid. So this is the syntax of copy constructor, and yeah, so we return the newly constructed object, and we return it again using ampersand. So this is about copy assignment. So this is copy assignment, this is not copy constructor. So basically what we did is we overloaded the equal to operator, right? This is equal to operator. Yeah, so sorry, my bad. This is a copy assignment function which we have overloaded because we are using equal to, and here earlier I said that the compiler will add its own copy constructor, right? And yeah, so this is a construction which is happening. This is not an assignment. And why? Because you have p2 which is getting constructed for the first time. Okay, and since it is getting constructed for the first time, we are actually using a copy constructor and not a copy assignment. Okay, so if I write something like unique ptr and p equals p2, p2 is already sorry, we will not declare, we will do something like this, which is a assignment happening. Okay, and this is assignment because p has been already constructed. Okay, p is not being constructed for the first time. Here we will have a copy assignment. So basically we overloaded the equal to, and we are here, right? Just let us return this, whatever let's say this object, we took p object, right? And all the member function of a class by default get a function parameter which is this. So we are going to return this, but since this is a pointer and once we dereference it, it will be object, right? So this is basically the copy constructor, copy assignment. Let us add cout copy assignment. Okay, and now we will see that it prints copy assignment because we invoked it from here. Now let us invoke for this the copy constructor. So we will see what is a constructor. Constructor does not return anything. Copy assignment will return, it will return the this pointer object only. And why? Because it may be further used for further chaining. Okay, so unique pointer will again take a unique ptr p, and let us say that we are doing a cout copy constructor. Okay, so now if you see, it is printing copy constructor first for this particular, and here it is happening copy assignment, right? Now one more thing, so whenever you do a copy assignment, we don't want to change the state of this ptr. For example, this unique pointer ampersand p, so p is something which is this, right? Now we are using this to copy to p2, but we don't want to change the values of p, right? So we take it as a const. Okay, this is the standard no syntax. So let us come back to our original problem, that we don't want the copy constructor or even the copy assignment to run, because unique pointer has a unique ownership. So what we will do is we will delete this. We will say that this is equal to delete, and this is also equal to delete. And by doing this, we have enforced that this is my unique pointer, and you cannot copy it. You cannot, create a assignment from this. You cannot create your own and reassign even, right? Here it was trying to create, and here you're trying to reassign. You cannot do that. Okay. So we deleted the copy constructor. Now the object cannot be copy constructor. Okay. And we also deleted the copy assignment, meaning the object cannot be copy assigned. Okay. So all these two instructions at line number 37 and 38, they become illegal. Okay. Okay, so I think you understand why we deleted the copy, right? Because we wanted a unique ownership, right? Exactly one owner has to be there. There should be no accidental sharing. And also, we will avoid the double delete risk. And this is the design of the standard unique pointer, right? So we are building our own unique pointer, and we are taking the inspiration from the standard unique pointer behavior, right? But now the question is, if we are not allowed to copy construct, copy assign, then how do we transfer the ownership? Let us say we want to transfer the ownership to P2. How do we do that? So for that, we use the move semantics. It means move semantic enforces that the ownership can be transferred but not copied. Okay, it means that if the resource is moved from P to P2, then the source, which is P, it will lose ownership and the destination will get the ownership, right? It means that we need to implement some kind of move, either move constructor or move assignment. Okay, so now let us implement the move constructor. Okay, what is a constructor? Constructor does not return anything. Unique ptr, fine. What does a move constructor takes as an argument? It takes a r value reference. How do we denote r value reference? We denote as using double ampersand. Okay, so basically this will accept a reference, and which will point to r value. Okay, we have not used single ampersand. Single ampersand is a L value reference, meaning it will point to some value which has its own memory. L value is something which has its name, it has its memory. Now we are taking the r value references. Okay, and inside that, two things we need to do. We need to make destination the owner. Okay, so first what you do is we say that, okay, whatever the other have, let us just copy to ptr of okay, and yeah, this is ptr, right? So now we have copied it to our this ptr, and that correspond to p2. Let us first comment it to avoid the confusion. So now p2, this is basically p2.ptr will now point to the p1.ptr. Okay, now what is the second step? Now we want to invalidate the source, right? So the source will lose the ownership, right? That is the need. Okay, now what is the source? The source is this thing, right? What if I make it a null pointer? If I make it a null pointer, it means that the source pointer will no longer be pointing to that heap memory. Now only the pointer of p2 will point to the heap memory. Fine. Just one more thing here. Let us add a print out move constructor, and if you see, it is taking a r value reference, and we cannot pass this as a l value. We need to use a move which will convert it from l value to r value. Okay, I think this much is fine, and then let's print. Now this p is now, it is pointing to a null pointer, so cannot dereference it. Let us dereference this thing, and we get a 10, right? So we have enforced the unique semantics here, and we have used move, which converts the r value to l value reference. So move does not move by itself, it is just that it will convert the l to r, and the move constructor can actually use this r value and do the ownership transfer. Okay, now if you see, we don't see the issue of double delete. And why is that? Now when p2 is deleted, the constructor will run. Okay, let us see out this. I am deleted. Okay, so now when the program runs, it says you I am deleted, I am deleted, I am deleted. Okay, so let us understand. Just add a new line. So this the constructor is running 3 times. So the first one is for p, the other one is for this book ptr, and then for its p2. But we don't see a double delete problem, and that is why, because when it runs for p, which now has a null ptr, and when you do a delete on null ptr, it is safe in C++. You can do multiple number of times the delete on null ptr. Okay, it is not undefined behavior. Compiler will usually optimize this because you are doing a delete on null ptr, so that is not an issue, right? You're not actually doing double delete. Okay, now we need to add one more thing here. So this is a move constructor, right? And we want our move constructor to be something which does not throw, meaning it should not throw an exception, which we signal by saying that this is a no throw. Sorry, this is a no exception. No exception. And this is the standard semantics of a move constructor. Move operation for smart pointers should usually be no except. Okay, and the reasoning is like, you have many standard, you must have used many containers, be it vector, and so vector, whenever you are using, they prefer move only if move is no except safe. Like if move will throw, then the compiler would fall back to a copy behavior in some cases. Okay, so basically move needs a guarantee that, okay, I am now moving things. If there is an exception, then it will create an inconsistent state at both the source and destination. Let's say you have to move 10 blocks from A to B, and you are using the move. So you move the first 5 blocks from A to B. Now let us assume some exception happens. Now both A and B are in inconsistent state, and you cannot go back to the original state. Okay, so if you give the compiler a guarantee that, hey, this is going to be a no exception, then only the compiler will use the move. Otherwise the compiler will say that, okay, since you are not very determined that this is a candidate for no except, I will use copy, meaning I will copy the blocks from A to B. I will copy first 5 blocks from A to B. If exception happens, the A is still consistent, right? So I can just do the undo, and we will have a consistent the state which was already existing. So if move may throw, the container may fall back to copy behavior, right? And now that we have written no except, meaning for this unique ptr class, moving is just safe, just pointers transfer, and there is no exception that is going to happen, right? It is just that we are doing some kind of copying of pointer. Basically a pointer transfer is happening here. Okay, so it should not throw, and that is why we have written that, hey compiler, this is no except, please be assured that this is no except. You can do the move operation, you don't need to fall back to copy operation. Now that we have added the move constructor, let us add move assignment also. So for move assignment, we know that we will return a reference for further chaining, and we will overload the equal to operator. We will not change whatever you are giving. So let's call it okay, now this was move, right? So if assignment will happen, we are definitely going to change the source, right? So the syntax will be different from the copy assignment. In copy assignment, if you remember, we use a const, but in move since the very behavior is that the source will be modified, we will not use const. Okay, so we will say that okay, unique ptr, it will take a r value reference. So this is the other, or this is the source, and we will say that okay, this is no except, so don't even try to fall back to copy assignment. Fine. Now let us do some assignment. Now I am trying to do move again the ownership of p2 to p. Okay, now let us see what happens. Right now it is giving us the error that use of deleted function, this is a copy constructor, rightfully so, because we are passing the r value. Okay, so this particular statement is nothing, but we are saying that you do p and then function is operator equal to, and then we are passing p2. This is what is happening, right? Okay, ope, I don't know the spelling of operator, ope rtr. Okay, so these two are equivalent. Okay, now you need to use a move here to get a r value reference which our move assignment will accept. Okay, also let us add something which is move assignment. Okay, and then we are going to return this whatever you have sent me. Okay, now let us try to implement the internals of move assignment. Remember what we wanted. So our destination should be honor, source should be deleted. This is what we wanted, right? Okay, so we are saying that you do this is this ptr should be equal to other dot ptr, right? And other dot ptr should be equal to null ptr. Okay, fine. Now we need to print p only, because p2 is now pointing to null ptr. Because we made p2 will come here, and p2.ptr is null ptr, right? So we have implemented the move assignment also. Okay, now one more thing. What will happen if I instead call let us call p2 here also. Okay, you call p2 here also, then what will happen? Now if you see this, okay, so we are doing a move from p2 to p2 only. Okay, so what we are doing is we are just copying this will have no effect, and then we are making it a null pointer, and so we cannot dereference a null pointer. Let us just comment that. Okay, so if you see here, this will invoke a move assignment. It comes here and it does this thing. Okay, how do you prevent this? How to prevent self move? So what do we want? We want is if whatever this is pointing to, if this is not equal to this other pointer, then only you do all these things, right? This is what we want. Okay, and so this will ensure that when you are trying to do the self move, it will not happen. It comes here, it printed move assignment, it will not do this because the check will fail. This is the same as the other pointer. Okay, I mean the pointer that we get from ampersand other. So now this is done. And just a small thing again, since we are very much concerned about memory leak, what if what if this pointer was already pointing to something? What will happen then? If this is already pointing to something and we will assign the ptr value, then now the ptr will point to a different location, meaning the old location object is not free yet. It will cause a memory leak. So before even pointing to the different location, we would want to delete it first. So, and this is generally a very safe mechanism, that before taking a new resource, the current resource must be released, right? Because we are dealing with unique pointer. Now if you are going to point something else, first delete what you were pointing, otherwise it will cause a memory leak. Okay, so this is done. Now let us try to implement all the other functions which the standard unique pointer has, and it is a good way to practice, and it will also it will actually remember stuffs and remember the standard functions that the unique pointer has. So unique pointer has a function called release. What release does is it will return you the raw pointer. It will stop owning the raw pointer, meaning uh, it will not delete it anymore. Okay, so now the caller is responsible for delete. Okay, so let us implement release. So what I'm saying is, give me my pointer back. Release. Okay, let us call this release on p2. Okay, and so this should return me the pointer, the raw pointer which p2 is having. Okay, so let us just implement release. It should be pretty much straightforward. I'm returning whatever type you are sending me. I will return a pointer to that. I will say release, and so let us create so what we will do is, we will say that now this object pointer will no longer point to something. Okay, I'm releasing it and I'm giving to you what. Okay, before releasing that, let us just store it somewhere. I said that okay, the start temp equals to your ptr, and once I delete, I will just return the temp. Okay, now if you see it here, you have a if you do a cout to post release, what you have is raw. Okay, print raw and post release. I mean, just to differentiate, this is there. Okay. Okay, so now if you see, you are able to use this dereferencing on raw. Now p will not point to anything. Okay, now it means that you have to manually delete it. Fine. Okay, after release, the smart pointer will no longer own the object. Now if you forget to delete, now leak will happen. So release has to be something which has to be used in certain circumstances. It's kind of an escape hatch, I would say, not an everyday tool. Okay, now let us add reset. So what does reset do? Reset will just destroy the currently owned object, and meaning the memory from the heap will be deallocated, and the current ptr will point to let's say whatever the new pointer that I'm giving it. Okay, basically it should reset the value. Okay, so what I'm saying is, let us do for reset. So I will say that, hey p2, please reset yourself to this new value. Okay, this is simple to implement. Why? Because we are not returning anything. Okay, we are just taking this new ptr. Okay, we are deleting the old ptr, remember, and we are saying that okay, now I will deleting the old ptr, and now the old ptr will be new ptr. So basically I am resetting the value. Okay, just do print post reset. This would be our overloaded asterisk operator. Okay, oh, so okay, post reset is 20, post release 21, so this is fine. Let us just remove these. I'm not liking them. Okay, okay, so we have now done the reset. Okay. Now what happens if we do p2 dot reset without any without passing anything? Okay, so it will obviously complain that there is no function which is taking void, I mean zero argument, because you have a reset but it takes one argument. Let us give it a no default for now. Let us add a what is the problem? So we have said that if there is no new ptr, let us assume that there is a null ptr. Now if you reset it, obviously you are going to see that error, because now it is going to invoke, you are trying to dereference it, but it points to a null ptr because we have reset it, and hence it will give error. Okay, just comment it. Okay, okay, now let us add one more feature. So let us add a operator bool. Okay, this will ensure that the smart pointer that we have can be used in condition. Okay, so something like if p, okay, something like this. Okay, so if p, then we will say that cout condition on smart ptr. Fine. Now how do you implement this? You are saying that if p, basically it is trying to check if whatever inside this parenthesis is it true or is it false, and hence you see there, right, could not convert p, which is a unique ptrp int, to bool. So it means that we need to overload the bool operator, right? So I say that, okay, so you have an operator, let's say bool, which I need to add. Okay, and so it should just return that this ptr is something, this ptr is not a null ptr. Okay, and this ptr. Okay, now this is returning as true because we see that okay, it is not printing condition. Okay, because we called on p, right? Let us call on p2 because p is already moved from, so it won't be there. Let us do on this. So once we do on p2, it goes and check this bool. So we implemented this function bool. Okay, and this is fine. Okay, now one more important thing, we want the controlled conversion to bool. Okay, we don't want some implicit, some weird conversion. We want to explicitly say that, okay, see, if this is not, this pointer is not a null pointer, return me bool, return me true. That is the simple thing we want to do. So we don't want the compiler to do some kind of implicit conversion to bool. Okay, so that is why a good way is to always include explicit. So you explicitly are doing a conversion to bool. Okay, this is fine. Also, don't remember to add const because we're not changing anything to this operator. Remember to always add explicit because we want the controlled conversion, not some weird accidental implicit conversion by the compiler. Okay, now let us say that I created a unique ptr int. Okay, and this is p3 and this is new int 50. Now I want to swap the values of p3 and p2. Okay, so what we want is we will take this p2 and we'll call swap p3. This would swap the pointers, the row pointers from p3 to p2 and p2 to p3. Okay, this is what we want. Let us just implement this. We will write a simple swap function. We're not going to return anything, we're just going to swap it. Okay, so we take a unique ptr reference object, and again, now you are swapping things. Okay, you don't want to swap partially, you want to maintain a consistent state. Whenever there is a compulsion, there is a need of being consistent, so that partial operation does not leave you in something from where you cannot recover. So better you hint the compiler that, hey, this is a no except. Okay, you do the swap by move, you don't do like a copy swap. Okay, so now we will use our standard swap that comes with the C++ library. So I say explicitly that, hey, swap, you just swap whatever this ptr has and whatever this other has the ptr. Now it is swapped. Okay, now if I print p2 now, post swap, it will give us star p2, it will give us 50. Okay, so we got some good ptr, got some good unique pointer, but it is not close to the standard unique pointer that we have, that is implemented inside the memory header that you need to include. We're not even close to that because we have a lot of missing things, including let's say custom deleter, make unique, array specialization, empty base optimization, all those things. So let us implement those also. So just to summarize, we have built the first real version of unique pointer from scratch. So at the core of it, it is just a class holding one raw pointer. Its constructor captures ownership, its destructor releases ownership. Then we made it a pointer like using operator, asterisk, other operators that we overloaded. Then we deleted the copy operations because we want a unique ownership, okay, and so the unique pointers cannot be copied, so when we enforce that, then we added move constructor, move assignment, because ownership can be transferred. Then we added release, reset, swap, boolean conversions, okay. So now our object, unique pointer object, is not just a wrapper. It actually behaves like a real resource owning, resource acquisition type, okay. Now let us continue. We will add our custom deleter. We will add make unique and then see what happens, okay. So we will add a custom deleter, meaning the cases where delete p will not work efficiently, will not even be supported syntactically or even semantically. We want our own deleter. We will not rely on the destructor delete ptr, okay. Okay, so now let us assume that before we go and implement anything, let us use the standard unique pointer and try to understand how deleter works with, how custom deleter works with, standard unique pointer, okay. So let us add a new source editor here, and for this let us add execution here, and this is pointing to here, okay, fine. Now let us create a unique pointer, unique ptr int p new and 10. Then let us include stream, and for unique pointer we include the memory header, fine. Okay, now let us print cout. So this is the standard unique pointer which is from the memory library, and we are printing ptr, okay. Now to this unique pointer, which is the standard unique pointer, how do you pass a custom deleter? Okay, so understand that how we pass deleter in this standard unique pointer, right? And then we can reverse engineering, and then we understand how in our custom the class for unique pointer that we have written, how can we use custom deleter there, okay. So right now the deleter is, whatever unique pointer has its own deleter is running. Let us assume, what if we have something like a file object? Sorry. Let us say we are opening a file in read mode, okay. This is file open. I mean, just understand that we are now not dealing with integer, we are now dealing with a different kind of object, and this object now will not you cannot just do this unique pointer unique ptr. Now the type is file, and we say f ptr, and we pass f, okay. Now if you see, we have not got any error, okay, and but we had a file connection established, but whatever this unique pointer is doing, that is definitely not closing this file, okay. We have opened the file stream, but we have not closed it, okay. It must be doing internally some delete ptr only, okay. So as for integer, it will do some delete ptr. So for this file also, because this is pointing to some memory, right? So again it will do delete f, okay, delete f ptr, and it will compile, but it is logically wrong, right? It can even have some undefined behavior at the runtime, right? So in cases where delete ptr will not work, we need to provide a custom deleter, okay. Now so let us try to add a custom deleter, and then we will see how it runs, okay. So first write our deleter. Let us use a lambda, okay. So we say that my deleter is nothing, it is not capturing anything, it is input, it will take the same raw pointer which it need to handle, okay. So this is, and what did we want? We want is, so let us first write that we want to close the file, okay. This is what we wanted. So we will do f close of f, fine. Now this is the ideal way we want this resource to be deleted, but since unique pointer is using its own custom deleter, its own internal deleter, it will not do in this manner, and you can have a runtime undefined behavior, okay. Now let us pass this deleter into our unique ptr, okay. Let us pass this unique ptr and deleter delter, okay. It gives error that deleter So we are getting an error. Let us try to understand what is the error that we are getting. Okay. So if you see here, we have a auto deleter. This is a lambda. Now, if I ask you what is the type of this deleter, example, when we have, let's say, class A, and so this is, and I, let's say, create an object of this class, A class, then do you know, right, that the type of the type of object that I will create is of type A, right? But with auto deleter, with this lambda, it creates an object of some, anonymous, unnamed lambda type. Okay. And the template needs, since the template is instantiated at runtime, at compile time, it needs the name of the type. Okay. Deleter is not a type. Okay. The compiler wants to know that what is the type of your deleter. Okay. So you use that function declare type, and then we'll say that type is the same as which is the type of this deleter. Fine. Now let us see how this our deleter runs. It is printing 10. Okay. So since I'm running this inside the online compiler, let us not try to read but try to write also. Then maybe it will create the file, right? Yeah. So earlier I was trying to read, but since I'm an online compiler with its own virtual environment, its own environment, and in restricted mode, it was not reading the file. Now if you see, this f is pointing to the file, and I created a unique pointer for this file, and we passed a deleter. What is the type of deleter? We don't know. So hence we said that since this is a lambda anonymous types, I say that okay, listen, this is the declare type of deleter. Okay. Because the lambda creates closure objects, and but we don't know the type of those objects, hence we will write declare type. Okay. And we pass the actual deleter. Okay. So now if you see, it is printing 10, and it is also printing close the file. Fine. So this was using lambda. Now let us also use, let's say, a normal, function. So we'll just write a function which will not return anything. It is my file deleter. It will take a file pointer, and what will it do? It will just check if you have a file, and if you have a file, I'm saying that okay, file deleter. Okay. And then I will f close it. Okay. F close the file. Okay. Fine. Now I create a unique pointer, and we pass, now that we have a function, it's not anonymous function, we will pass the file deleter here. Okay. So, and okay, now we are passing a file deleter. What is the type of file deleter? What is the type? This is a function pointer. The type is known. This is a function pointer. How do you write a function pointer? So the function pointer for void is simple. You say that I'm not returning anything. Okay, then are you taking any argument? Yes, I'm taking any argument. The argument is file. Fine. Then this is a function and a pointer, function pointer. So I'll say this is a function pointer. This is return type. This is the parameter, and this is the this represents that this is a function pointer. Okay. So this fine, f is not okay. This is p. So now we have a custom deleter. We have a custom function deleter. Fine. Okay. So let us see what is the error here. fptr1 fptr f was not declared in the scope. Okay. Okay. So it is now giving a double delete because we first tried to delete using this, then we are trying to delete using this. Okay. So just comment it for now, just to see how the function based deleters ran. Okay. I see you have a function based deleter. Fine. Okay, now let us try to add a new, let us use functors. Okay. What are functors? Functors are nothing but they are the implementation or the overloading of the function call operator. So let us say you have a class A, and you have a, let's say, operator overload. What do you pass? You are passing file p. What are you doing? You're saying that if p, then this is a functor. Okay. And we will close the file connection. This is common. F close is there. Right now let us do this is there. just remove this and we will pass, just comment this out, okay, so that we don't have double delete. Okay, now with functors we need to pass the type. Type is a, okay, let us pass this. So we pass a type of a. This is not needed with functor, okay. Once you pass a type with a, it will understand, sorry, it will understand that okay, you have passed it a class which has an implementation of that double parenthesis, which is function call. And since you have that, this is a functor, okay, now you just need to use the class type and it will work like actual function. So when you say a, it understand that okay, this is going to have something like this, uh, uh, like this thing, like it is going to implement something, this operator, okay. And hence we don't, we don't need to pass it. What is this error? So we are providing a type a, and if okay, this is okay. So in this class we need to make it public, okay, then only it can be called from outside, okay. Now so this functor is called, okay. So we have seen three different ways to implement the deleter. First we use the lambda. Lambda does not have a type, so we used declaration type function. Then we had a function, and then for function pointer there is a type. Then we had a functor which specifically has a type a, okay. Okay, now one nuance that I want to cover here, if you see, for the normal function and for the lambda one we needed to pass the actual deleter, right? Now unique pointer must store the deleter inside itself, okay. And how it stores, it basically depends on the type of deleter. Whenever you are using functor, it works without passing deleter explicitly, okay. Let us assume someone gives you information that hey, a is a type of deleter. Now do you need any extra information? Is there an ambiguity that some other a will be there? There is no ambiguity, right? You said that okay, this is a, the type is a, there is only one class of type a, there is only one operator of function call operator overload inside a, so we don't need to actually pass the deleter, okay. So a is a type, and there is a clear explicit guarantee that there is no other type of a, and in a you will find your implementation of function call, okay. So now the unique pointer will default constructed internally, okay, and which should be like uh, something like it is internally passing, let's say something like this. So you have like a, an object of a, okay, and this is doing something like this thing, okay. And that is how you call functors, okay. You create object of this class and you can actually use it to, let's say this is the way you can actually use it to call, okay. And this is how functor is, okay. That is about this. And so but as I told you, you don't need to explicitly pass it whenever you're dealing with functors. In case of function pointer you must pass it because there can be multiple function pointer of this type, okay, which would be void and taking a file. So you need to explicitly say that okay, this is the type and this is the actual function, okay. And okay, and for lambda also you need to pass deleter. Why? Because lambda has a unique unnamed type, okay. The type is not default, generally it's not default constructible, okay. So for unique pointer to actually relate to it, you first need to pass a type and then the name of the lambda, okay. Okay, so just to reiterate, there are a few points that I want you to be mindful of. Usually won't need it, but for Adobe interviews at the level of, let's say, computer scientist 2 or maybe even 1, they may ask you with lambda, why do you need to pass this deleter when you're passing the type already? Because with functor, let's say you had a, you don't need to actually pass it here, right? The compiler does it internally. I mean, the unique pointer does internally something like this. It will do a, and it will be passed, right? So this is something which unique pointer will do internally, okay. Oh, what is the error? Okay, so the error is must be related to yeah, it is related to most vexing parts. So if you see here, compiler assumes that you're actually creating a function declaration which returns a type a, there's a function name, and it does not take any argument, okay. This is the most vexing parts problem. And so just use a universal uh, initialization and the error will go away. So now if you see, this is what the unique pointer will do internally. Whenever you pass a, it understands, okay, see, a is a funct, a is a class, and it has only one implementation of that thing. So I can instantiate a like this, and then I will use a. Okay, and but let us do one thing. Let us say that this is this, right? Let us add a constructor. Okay, and let us remove this thing. Let us remove this thing also. Okay, now if you see, it is failing. The unique pointer is not able to internally do those things which it was doing earlier. Why? Because now this a is not default constructible, meaning the default constructor of a has now been deleted because we defined a new constructor. Okay, and if I remove this, then the default constructor will be there. The unique pointer will internally create a default constructor of default using the default constructor object of a, and it will pass it here. Okay, now the problem with lambda is you have given a type decal type deleter. You might say that for this also the unique pointer must do something like okay, so first understand, whenever you declare lambda, what happens? Whenever you, let's say, where is it, lambda, this is the lambda, right? Whenever you declare a lambda is basically anonymous function. Okay, so the compiler will generate something like a closure object. So the compiler will say that, okay, you have a lambda something, lambda type, and inside that it will do this operator, and it will take this, and it will paste here, it will take this, and it will paste here. Okay, so this is what happens. This is what is generated by the compiler whenever you write a lambda. Okay, this is what happens. And now when you are saying that whenever you are now doing this thing, decal type deleter, and let's say you do not pass a deleter, okay, the compiler will throw error, obviously, and the same reason, because the unique pointer is not able to internally, no, let us comment, this is what happens internally, this is what is generated as a closure object. We should not write it as a code. Okay, so when you do this, when you remove the actual deleter, the compiler or the unique pointer tries to create a object. So we try to do something like whatever is the type of a deleter, you do something like object. Okay, this is what the compiler want to do, but it may not be allowed. Okay, meaning that lambdas are not default constructible. Okay, so at least they're not guaranteed to be default constructible. Okay, the compiler will assume that this is not default constructible, and if it is not default constructible, and just remember this case, it means that unique pointer will not then be able to create the object and then use it here. Okay, meaning you have to pass the deleter explicitly. Okay, this is fine. And then with file, it is pretty much obvious because this is just a generic file function pointer, right, which takes a file reference. So the actual deleter can be anything, right? So here too, you explicitly has to pass the file deleter. Okay, now this was the standard implementation, right? This unique pointer was standard. We have used it from the memory library, and we have used our custom deleter. But we were working on something where we have written our own function pointer. We're not even close, but yeah, this is a good pointer. I mean, if in interview you can tell all these things, that would be enough. But to implement deleter, what I want is, if you have really seen this video till this point, then I want you to comment in the comment section that implement the deleter, custom deleter for our unique pointer also, our custom unique pointer also. Okay, then only I will create the video on that. Otherwise, I think if no one is listening till here, then I think there is no point, right? Whether it's there or not there, doesn't matter. And when we will create our own custom deleter, that will then use concepts from template metaprogramming, and compile time optimization, template specialization, and all those sorts of things, which I think which is very important when in terms of explicit memory management, and in terms of low latency also. I mean, in HFT we use it a lot, and yeah, and you also get a clear picture of why do we avoid in a hot path, let's say, why do we avoid using virtual, right, instead of using templates. So all those kind of things, it would be a very great exercise, and for that you need a little bit basics about template, which I think we have already covered, right? So that is all for this video, guys. If you have really watched till this point, and then you know what to do, right, to get the other video. Okay, so thank you all for watching. Bye.